So today I want to complete talking about P, NP, introduction into NP completeness. And then the P equals NP question. Okay, so last time we defined what was meant by the worst case running time of a particular algorithm, and actually we're not talking in terms of algorithms, we're talking in terms of Turing machines in this class. When you get into a class like 122, then the language all changes to talk about algorithms and problems. Here we're talking about Turing machines. And we define something like this. Time, I may not have actually gone as far as to use this particular notation, time and k. That's the class of all languages that can be decided by a deterministic Turing machine whose worst case running time is bounded by a function of input size, we'll call it f of n, where f of n is big O of n to the k for some k. Okay? So, the worst case running time of a deterministic Turing machine, that's the, well, we're using time and number of steps interchangeably here, but that's the maximum number of steps that that Turing machine will take, the number of transition steps that that Turing machine will take on any input of size n. So we have a deterministic Turing machine, and it has input, and some of those inputs are of length n, some specific n, and then we can conceive of what's the maximum number of transitions that that Turing machine takes when it's processing any possible input of size n. And then that's the value for a specific value of n, and f of n is a function of those values. So we looked at that last time. So you have a particular Turing machine m, and based on the input size, there are various amounts of steps that that Turing machine takes on different particular inputs of size n. And if you look at this kind of complete plot, so conceptually, this is the set of all possible inputs. These dots represent all possible inputs to this Turing machine. And some of those inputs have length 3, some have length 4, some have length 5, and so on. And then f of n, it's the max for each of these. So this is what f of n is. As a function of the input size, it's the maximum number of steps that that Turing machine takes. Okay? That's f of n. And then we can talk about f of n, that function, is bounded from above the big O notation by n to the k. And we defined the big O notation last time. N to the k, that's a polynomial function of n. K is some particular number, 2, 3, 5.7, whatever. N to the k is a polynomial function of n. And so this is the time, nk, it's the class of all languages that can be decided by a deterministic Turing machine whose worst case running time is bounded by a function of input size, f of n, that's what this thing is over here, where f of n is bounded by some polynomial function. So, big O of some polynomial function. So, for example, this might be n cubed. Okay? So this f of n is bounded by n cubed. And we talked last time about what the big O notation means. So the n to the k may not always be bigger than f of n, but eventually it becomes bigger. Okay? Any questions on this? This is a bit of a review, although I'm not sure I used this terminology last time. Okay. All right, then P, definition, P is equal to the union of k time n to the k. So P, it's really that's the set of all languages which can be decided by Turing machines whose worst case running time is bounded by polynomial functions. Okay, so these are the good guys, in a sense. The good languages. They're good in the sense that for each of them, you can exhibit a decider, Turing machine. The decider can say reject or accept for any given input. And that Turing machine doesn't take too long. Its worst case running time is bounded by a polynomial function of k, as opposed to an exponential function, it's a polynomial function of n, as opposed to an exponential function of n. We talked about this last time. 2 to the n is an exponential function of n, and it grows much faster than, say, n squared. You might say, well, they both just have a 2 and an n. What's the big deal? These are very, very different functions. This one grows much faster than that. Although, as we discussed last time, for small values of n, okay, they don't look that different. Okay, but this is an exponential function. This is a polynomial function. And so here we're saying a language is in this class P if there's a decider for that language whose worst case running time isn't extreme. It's bounded by just a polynomial function. Now you might say, well, but a polynomial function like n to the 2 to the 60th. Okay, that's a polynomial in n, right? 2 to the 60th, I don't know what 2 to the 60th is, but it's a big number. And so n, that's still a polynomial, but it's a very rapidly growing polynomial. Still, the distinctions that we're going to make are kind of crude. It's between whether a language can be decided by a deterministic Turing machine whose worst case running time is bounded by a polynomial or not. Okay, so that's the crude distinction we're going to make, and we're going to just say that intuitively these are the kinds of results we want. We would like to have you'd like to be able to show that you can decide a language efficiently. So up to now, when we've been talking about undecidability, it's just whether a language can be decided at all or recognized at all by some Turing machine. Now we're talking about, can it be decided efficiently? And our notion of efficient is this worst case bound of polynomial time. Okay. All right. Then let me remind you about worst case time for non-deterministic Turing machines. So first of all, a non-deterministic Turing machine that is a decider must halt on every path in the non-deterministic computation. Okay, that's the way that a non-deterministic Turing machine decider was defined. Every possible, remember, in a non-deterministic Turing machine, the computation starts out with one copy of that Turing machine. But as the computation goes along and you hit a non-deterministic step, a place where the Turing machine can decide it can go in more than one way, it has more than one transition that's permitted, then the non-deterministic Turing machine, the way we've been thinking about it, is clones itself, and in as many different choices as there are at that point, and each one of those takes a different choice. So the computation, let's say if we have 3 choices at this point, we get 3 cloned copies, and they go make 3 different decisions as to what the next transition is. And so this computation looks like a tree, and if the non-deterministic Turing machine is a decider, every one of these paths has to actually halt. So it ends up with a reject or an accept. Okay? And then the non-deterministic Turing machine accepts its input if and only if at least one of these paths accepts, and it rejects its input if and only if every one of these paths rejects. Okay? This is just a reminder of what it means to be a non-deterministic Turing machine and what computation a non-deterministic Turing machine does. And because of that, we can now define the worst case running time of a non-deterministic Turing machine is equal to the maximum number of transitions or edges here on any of the computation paths. So if you on a particular input, so it's a particular Turing machine on input W. So here W comes in to this Turing machine M, non-deterministic Turing machine, and what happens in the computation is we get this computation tree, and each one of these paths halts. But let's say it halts there. The deepest of those, the maximum number of transitions, that's the worst case running time for this non-deterministic Turing machine on this input W. Okay? And then, just as we did in the case of a deterministic Turing machine, we can talk about the worst case running time as a function of input size. It's the same idea, because on any particular input, if we have a particular Turing machine M and we have a particular input, we now have a well-defined notion of what its worst case running time is on that input. And therefore, we can think of a graph like this that it's displaying all the possible inputs of all the possible sizes, and then we have a function f of n over the max. So we can talk about the worst case running time of M as a function of input size n, and that function is f of n, okay? And then similar to what we had over here, we can talk about non-deterministic time of n to the k, and that's just analogous to what we have here. It's a class of all languages that can be decided by a non-deterministic. So actually, instead of rewriting it, let me just go over here and change this. Non-deterministic time, n to the k, is the class of all languages that can be decided by a non-deterministic Turing machine whose worst case running time is bounded by a function of input size f of n, where f of n is n to the k. So it's very, very analogous. It's just that you have to be clear on what it means, what worst case running time means for a non-deterministic Turing machine, as opposed to a deterministic Turing machine. It may seem a little more complicated. Okay, let me just throw in one side comment here. When I talk about computations of a non-deterministic Turing machine, I've been talking about paths. This is a path down this computation tree, and that seems to be the appropriate term. For some reason, in the book, he talks about these as branches. Okay, not a branch, it's a path. Okay, this is a branch. At any rate, so just when you read the book, and if there's that little deviation in terminology, you'll understand that. Now, definition, NP is equal to union of K n time n to the K. This is actually not the first definition of NP that he gives in the book. We'll come back later and talk about another definition, but probably not this, maybe. At any rate, but I think this is the most natural definition, and it's the one that parallels P. So we're just saying this is the, well, we had the definition of n time n to the K over here, and now we're just taking the union over all possible K. Okay, so these are, you find all the languages that can be decided in non-deterministic time n, that's when K equals 1, all the languages that can be decided in non-deterministic time n squared, and so on. And K doesn't have to be an integer. N time 2.5, whatever. All the possible polynomials that, anyway, this is NP is the set of all languages which can be decided by some non-deterministic Turing, where each can be decided by some non-deterministic Turing machine whose worst-case running time is bounded by a polynomial. Okay? So, which of these classes, P or NP, feels more inclusive? I mean, is it harder to be, you just take some random language, does it feel harder to be in P or to be in NP? Or what? Anybody have any intuition about these definitions yet?
NP is more inclusive.
Who said that? Yeah, NP is more inclusive. Why? Okay. All right, so claim NP contains P. Okay, everything in P is in NP. Right? Well, actually, you should be able to see this just formally from the definitions without any intuition at all. Even if you didn't speak English. If you're just looking at these definitions, if you could read them and at least parse them, and you couldn't invest any particular meaning into these things, this should be clear. Well, I mean, maybe I'm exaggerating that point, but the point is that anything in P, okay, that has to be decided. Those languages have got to be decided by a deterministic Turing machine, whose worst-case running time is bounded by a polynomial function. Is a deterministic Turing machine also a non-deterministic Turing machine? Yeah, of course. It just doesn't happen to have any non-deterministic transition rules. All the transition rules are deterministic. Each transition rule gives you one choice only. So every deterministic Turing machine is a non-deterministic Turing machine. So if you look back over here at the two definitions, deterministic time just didn't have this n in front of it and didn't have this n here. So just from that formal manipulation, it's clear that everything in P is also an NP. So NP certainly contains P. All right? But I still want people to think intuitively about the different requirements to be an NP in terms of a non-deterministic Turing machine as opposed to being in P. Does it feel like it's easier to be an NP than to be in P? You use some language, and you have the task of trying to figure out whether it's in P. If you have that task of trying to figure out whether it's P, it means you have to come up with a deterministic Turing machine which can decide that language, and its worst-case running time. You have to prove that its worst-case running time is bounded by some particular polynomial of the size of the input. So that's your task. As opposed to show it in NP, you just have to come up with a non-deterministic Turing machine, which can do all the things that I said. It decides the language, and its worst-case running time is bounded by a polynomial. But the non-deterministic Turing machine can branch. It can branch at every node of its computation and make guesses and try things in parallel and so on. The total size of the tree can be enormous, exponential in size in terms of the length of the longest path. We only measure the total time that this computation takes by the length of the longest path, okay, and not by the total size of the tree. So if you actually talked about turning this non-deterministic computation into a deterministic computation, which we know how to do because we showed that that every non-deterministic Turing machine, for every non-deterministic Turing machine, there's an equivalent deterministic Turing machine, which simulates it. We showed that earlier. But if we actually did that on a specific computation, the amount of time taken by the equivalent deterministic Turing machine would be exponential in terms of the time that we're calling here, which is just the length of the longest path. Okay? So I'm just saying when we clock a non-deterministic Turing machine, we're only looking at the length of the longest path, and so that's a tremendous advantage that the non-deterministic Turing machine has in terms of its time, the time that's recorded, as opposed to a deterministic Turing machine. Okay, so I still don't see that people are getting a good intuition about which one of these. Would anybody like to respond to my general question of, yeah?
Well, I think it would be easier to describe something in NP than in P because NP includes P, and you have all these other options to make your description more flexible.
Yeah, I think if we did more actual problems of programming a non-deterministic Turing machines, which we didn't do much in this class, and the book doesn't do really at all, you would see how much easier it is to come up with Turing machines, non-deterministic Turing machines that decide languages as opposed to deterministic Turing machines. And when we put on the time requirement on top of that, you would see how much easier it is to come up with non-deterministic Turing machines whose worst-case running time is bounded by some particular polynomial, as opposed to deterministic Turing machines whose worst-case time is bounded by that polynomial. Now, we did see a little bit of the discrepancy or the differences between determinism and non-determinism when we were talking about finite-state machines. And I think we saw there how much easier it was for a number of problems to come up with a non-deterministic finite-state machine that recognized certain languages, as opposed to deterministic. So non-determinism is allowing non-determinism is a huge advantage in coming up with Turing machines that decide languages. And there are vast numbers of problems, languages. In this class we talk about languages, and in 122 we talk about problems. Vast numbers of languages that can be decided in polynomial time by a non-deterministic Turing machine, but we don't know a deterministic Turing machine that can decide that language in time bounded by a polynomial function of the input size. So right now, just in terms of our empirical knowledge, NP is this huge set, and P is a small subset of it. This is empirical. What I mean by that is that we have many languages that we know are in NP that we don't know whether or not they're in P. Okay? So not knowing is not the same thing as knowing not. Okay? So empirically, we know a vast number of languages which are in NP, but where we don't know that, well, we don't know if they are in P. Okay? So we don't know whether they're in P. That's not the same thing as knowing that they're not in P. All right? And, but we do know that P is a subset of NP. And so the open question in terms of what we've defined so far is the converse also true? Is NP a subset of P? Okay. Is it true or not true that if a language is in NP, it's also in P? That is, if you can exhibit a non-deterministic Turing machine that decides a particular language and its worst case running time is bounded by a polynomial function of the input size, does that necessarily imply that there would be a deterministic Turing machine that can decide that language and its worst case running time is bounded by a polynomial function of the input size? Okay? That's what this question says. And because we know this, and this is, if this was also true, then it would follow that P equals NP. And so this is often just stated as P equals NP question. Okay, is it true or not that P equals NP? Now, I'm sure all of you have heard of the P and NP question. P equals NP. There's a list of the most important open problems in mathematics, 7 or 8 problems on it, that you see every now and again on NOVA or equivalent kind of programs. And there's also a $1 million prize for anybody who can solve this question. What you probably don't yet see is why this is significant. I've shown you enough that you can understand what the question is in its full rigor, but you don't yet see why this is a practical significance and why it's important. Okay. What I'm going to do, I've got 5 minutes left. I'm going to push on with the next part of this, and then Thursday we'll solidify why this is important. And also in 122, if you take that class, or maybe some of you have already taken it, which is, of course, on algorithms and algorithm efficiency, you get back to this issue and talk about it in much more practical terms. But in 122, we always say, well, if you want a precise definition, you have to take 120. Well, I've just given you a precise definition. We'll do another version of that next time as well, which gives you a somewhat different sense of what it means. But this is absolutely precise of what the class P is and what the class NP is and what the question of whether P equals NP is. Okay, so let me just write down the next really important definition, which is polynomial-time reduction. Well, we've studied reductions. In fact, you've just studied, hopefully, about reductions of Turing machines for the purposes of proving undecidability. Okay? So we know in general what a reduction means, of being able to reduce one language, the question about one language, to a question about another language. Okay? One language to another. But now we're going to add, so let's say A language A reduces to B. It means that you have in here a Turing machine for B, a Turing machine that can decide B, and you want, actually this is the whole big thing, you want a Turing machine that can decide A. And what it does is it takes in input, this Turing machine that decides A, and it does something on W to produce, let's say, a W bar, and then it feeds that W bar into the Turing machine for B, and then based on accept or reject, then it accepts or rejects W. I didn't make this connection here because it isn't necessarily that accept of B is accept of W. We've seen cases where that it goes like that. We've also seen cases where it crosses. Accept out of B means reject, and so on, for A. But the point is that you can use B in here to build up a Turing machine that decides A. But this stuff in here, this do something, that has to be done by this Turing machine A. But we never said it had to be done fast. We just said it had to be done, you just have to show how it can be done by a Turing machine. And now we want to add on the requirement that the number of steps in that part is bounded by a polynomial function. Well, it's bounded by n to the k, where n is the length of W, that is the input to language A. Input to A, input to the Turing machine that we're going to be building for A. So now we're saying, yes, we reduce language A to B, but we better do it fast. Okay? And that's what a polynomial time reduction is. Okay? Do I have one more minute? Okay, that's a polynomial time reduction. We'll talk about, I'm so close to talking about NP completeness, but we'll do that next time. I just need another 30 seconds for that. I don't think I have it.